Kita, yes, we are live.
Yeah. Good morning, everyone. Welcome to this webinar on physical sciences winners today. As you, most of you are following the CSIR website and CSIR social media, must be aware that we have been doing this Swarup Bhatnagar Award winners. We have been bringing them to you almost every Saturday. So we have conducted webinars with the biological sciences and with medical sciences and chemical sciences winners. And today we are going to bring you the winners of the physical sciences category, Professor Rajesh Ganapati and Professor Surajit Dhara. Congratulations to both of them firstly on winning this prestigious award. And so those of you probably who are joining for the first time this webinar series, Shanti Swarup Bhatnagar Awards are one of the most prestigious awards in India, and in popular culture it is known as India's Nobel Prize. And so this opportunity, this COVID has actually, one of the benefits of COVID, if I can say that, is the access to people through this webinars and through online medium. And so we have used this opportunity to bring the best of India's science to you in different categories. So this is one such effort in that direction. And the idea is to take the science in the labs and take it to the common people as much as possible. Science is a very complex matter, and I think even among scientists, understanding other person's science or other discipline is very difficult. So this is just a small effort towards this direction to breach those barriers and see if we can communicate and ignite the interest of people in science. So I'm very happy to see that all our laureates of Shanti Swarup Bhatnagar have been readily participating in this webinars, and I thank them for taking their time and being with us. And before we actually jump onto the talks, I request Dr. Shekhar Mande, DGCSIR, to give his opening remarks.
Thank you, Geeta. Very warm welcome to all of you for today's webinar. As Geeta has already mentioned, Shanti Swarup Bhatnagar prizes have some iconic value in Indian society. They're considered to be the highest recognition for a scientist in the country, as Geeta already mentioned. And we're very happy that this year's Physics Award have been given to Professor Dhara of University of Hyderabad and Professor Ganapati of JNC ASA. So congratulations to both of you from all of us. And Indian science actually looks forward to much deeper contributions from both of you in the coming years. As I've been telling the previous awardees in biological sciences, chemical sciences and all, that is only the beginning, and your contributions actually will only start counting from now, that how deep you can actually take Indian science to. And we all look forward to you for taking the science further. For the general public here, we have been trying to bring the best of India's science to you through this webinar series. And what a better way than bringing the current year's Bhatnagar laureates to all of you. And Geeta has already thanked both of you, but let me also thank you from CSI side for having agreed to speak to general public today. And this is one way that we tell students across the country, faculties, and even the general public what excellent or outstanding science is supposed to be. And that's why Bhatnagar laureates actually come here and talk about their own work here in a language that is understandable to many people in the society. So we look forward to you come here and talk about today their own work here. It has already mentioned in a language that is understandable. The COVID period has changed so much. Society. We would have loved to have you in person, talking in some of the other institutes across India, but because of COVID, we are doing it online. But COVID has also brought science and technology to the forefront. So I don't think the science and technology has got as much traction in society as in the last 8 or 10 months. You very often see many of the leading scientists on television, in press, and many other places. And you also often see people on the street talking about the new vaccines, the new diagnostics, and the ways of combating COVID and so on and so forth, which actually bodes well for science, although the disease is terrible. So the science, bringing science back in focus actually is a good thing that has happened in the COVID era. But we do look forward, as I said, to many contributions from both of you, Dr. Ganapati and Professor Dhara, and I look forward to your talk today. Welcome to this webinar once again. Gita, back to you.
Yeah, thank you, Professor Mande, for those welcoming words and for always being with us for all the webinars and promoting the science communication efforts at CSIR. And so I'll give a brief introduction to Professor Rajesh Ganapati. He is currently professor at JNCSR in Bangalore. He obtained his PhD in physics from Indian Institute of Science in Bangalore in 2007. After that, he was a postdoctoral fellow in Department of Physics at Cornell University, New York, USA. And then he's been, from then on, from 2009 onwards, he has been at JNCSR in various capacities. His research interests are in the area of soft and active matter. And his current topic of study includes colloidal suspensions, gels, glasses and active liquids. I will not go more into the details. I think we will hear from Professor Ganapati himself. And a small request to Professor Ganapati, because our audience may be very diverse, if it's possible to make it as simple as possible, because I myself am lost when I'm reading at your research interests. It's very complicated. And also it will be nice to show where these areas would be interested in common life, like, where exactly the applications of your research would be. If you can throw some light on that, that would be highly welcome. Over to you, Professor Ganapati. Thank you.
Thank you. Thank you so much. Can you see my screen?
Yes, we can.
Okay. All right. At the outset, it's both a delight and an honor for me to be part of this webinar series and trying to get science to the maximum amount of people possible. So let me thank Dr. Mande, Dr. Geeta and Dr. Mahesh for this wonderful arrangements. So the story that I want to tell you today over the next 25 minutes or so is something that's been evolving in our group recently, and that's got to do with active matter. Okay, and what you're seeing in this video, in this background, are basically particles that are being driven, and you will see this sort of beautiful collective patterns that emerge. You see the swirls, these vortices. And I will try to tell you about what makes this system interesting, what motivates us to study systems like this, and then a brief summary on what we recently found in this particular system. Okay, so before I get going, the first thing that I would like to do is to acknowledge the people. So pretty much everything that I'm going to tell you today is work done by one student, Pragya Arora. She's here. And my journey in science for the last more than a decade in my group has been so much enriching because of all of these wonderful people that I've had to work with. I have this very long-standing collaboration with Professor Sood, which has been very fun and enriching. And of course, thank my institution and also DST for all the research support they've extended to me. Okay, so let me start by showing you a video of something that's pretty amazing. And what you're seeing here is something that happens at dusk. And these are birds called starlings, and they are native to both Europe, Asia, Australia. And what you see here are these beautiful collective patterns that emerge. Okay, and these starlings, so these are so the range of biological senses is pretty limited. But if you see this sort of collective organization that you see here, it's extending over kilometers. Okay. Now, the thing is, what makes these sort of patterns emerge? And this is not just restricted to starlings. For example, you can have army ants, which basically, so these are army ants, which are naturally blind. And when they lose their pheromone trails, what they end up doing are to just follow each other, and they spontaneously form these sort of spirals. And the really amazing part about these spirals is that this spiraling behavior is going to continue until all the ants die of exhaustion. So they just keep doing this, all right? And so these are naturally blind army ants, But that's not limited to ants. For example, these are people in a heavy metal concert, and you will see that these people are blinded by excitement, and they form these sort of spontaneous swirls once again. All right, and this, in fact, this physical understanding of why this sort of patterns form is actually a result that was published in Physical Review Letters. It's a very prestigious journal in physics in 2013. Okay, so so I've shown you birds, I've shown you ants, I've shown you human beings, and of course it's not limited to that. You can also see this sort of patterns emerge. For example, these are E. coli at very high densities, and you see these spontaneous swirling patterns, and these are basically fish schools. Okay, so all of these systems that I've been talking, that I've been giving you examples of, are basically come under the umbrella of what we call as active matter. And by active matter, I mean that these are systems in which they have some internal machinery to generate, to consume energy and generate locomotion. And the key thing to realize is that the direction of locomotion is not set by an external field, but it is set by the individual particle, be it a fish, be it E. coli, be it humans. It's the direction of motion is decided by the active agent. Okay. Now it turns out that if you want to see this sort of collective behavior emerge, then there are very simple rules. And in fact, in 1987, Craig Reynolds did a simulation. So you can download this app and run it on your computer for different parameters. And what he figured was that there are just 3 rules that give you this sort of beautiful collective behavior. The first thing is that the first rule is basically that you don't come too close to your neighbor, so you avoid collisions. So you have a finite separation. The next rule is that you roughly align yourself along the direction of your nearest neighbors. So if your neighbors are oriented in a particular way, you try to align best in that particular direction. And the next thing is you try not to steer too away from this group from your group. So you are drawn to your group, but you also don't come too close to them. With these 3 simple rules, he basically ran the simulation, and you see this flocking behavior. Okay, so these are just objects that are interacting via these 3 rules, and you see this flocking behavior. And you will see in a little bit that when you put in an obstacle, how these flocks fragment, how they avoid these sort of obstacles is something that you also see. And in fact, this precise set of rules was what was used in this movie Lion King. So if you've seen this came out in the late 90s, and you will see that now there'll be a stampede, and I'll just let the audio play because it's beautiful. And you'll see that these wildebeests are basically just running down this hill, and they are governed by the same thing. Okay, Okay. So the key thing to note is that the collective behavior that we are seeing here emerges without any obvious leaders or an overarching plan. There is no central command telling any particular entity to go in a particular way. This is just behavior that emerges naturally in a system of in a system that's driven, in a system that finds a source of energy inside and converts it to locomotion. Okay. Now, why should we study active matter? And as you will have already noticed, this is a very different state of matter because there is a continual consumption of energy that either manifests as locomotion or it exerts stresses on the system. So this is a system that's constantly consuming energy and dissipating out. And so this is a state of matter that's always out of equilibrium. This is not like the conventional condensed states of matter that we are familiar with. A biological cell is an active broth. For example, there are motor proteins, there are all sort of active filaments inside. And so how these sort of, how the activity in these sort of systems come together to understand how cells locomote on a surface, how cell division happens is something that's that comes under the umbrella of active matter again. Now, it's not just these examples. For example, there was this beautiful study that came out about 2 decades ago, in which they basically tried to find out that if you are in a room and there is a sudden fire or something, and you try to escape out of this room, they were able to model all of these. So each individual red circle that you see here is basically an active particle, and how active particles come out of an opening. Okay, so and they basically said that if you have rooms designed in a particular manner, you can avoid these sort of panic and stampede. So studying active matter also sheds light on crowd control, pedestrian traffic, and so on. And so we all keep reading about how we're going to have autonomous cars and machines, and studying active matter, learning from active systems is going to shed light on how you can avoid collisions. Also enable us to control robot swarms and so on. Okay. Now the examples that I gave you earlier on were all in the natural setting, and if you want to do controlled experiments in a laboratory where you can start trying to understand what are the essential features that give rise to this very rich behavior, you need laboratory mimics. And for the rest of my talk, what I'll try to tell you is what our approach has been in this direction. Okay, so the system that we are going to consider is very, very simple. Okay, so we're just going to take a bunch of particles. We call them granules. Granular matter is basically particles on the size of millimeter or so on, or millimeter or larger. So we're going to take these particles, we're going to put them on a plate, and what we're going to do is we're going to drive them through this device called as a shaker. Okay, and we're going to basically impose a particular waveform to the shaker, just an oscillatory waveform, so that the shaker plate moves up and down. And we're going to image these particles using a camera on a computer. Okay. Now, just to tell you briefly, so you have vertical oscillations, and this is particularly the waveform of the oscillations that we are going to use. And so the non-dimensional acceleration, so the acceleration here is just x naught omega squared. So the non-dimensional acceleration with gravity acting on the particles as well is just x naught omega squared by g. Okay. Now, what people have found and what many studies have relied on is that when these particles have asymmetry either in their shape or in their friction coefficients. So by that I mean that if you have a particle in which the tail of the particle has a different friction coefficient compared to the head of the particle, and you set these particles in oscillation, what you end up seeing are these sort of beautiful flocks, that naturally emerge in this particular system. Okay, so the key thing to note here is the vertical oscillations of the plate are basically the nutrient or the fuel that's being provided. And since the plate is driving each particle at the individual level, the direction of motion is set by the particle and not by anything else. Okay, and these are 2 examples that people have been that have been heavily investigated, in which you have these sort of disks in which you have a friction and a mass anisotropy, and you basically start seeing these sort of beautiful flocks, just like the ones that you saw in the videos that I showed you earlier. And this is work done by the Dosho group, and this is the system that's been well studied by Ajay Sood and Srinath Ramaswamy's group, in which they have a particle with a shape and a mass anisotropy. So you have this sort of tapered shape, and you set it in motion, and you will see these flocks again emerge. Okay. Now the thing that we would like to do is in any condensed state of matter, the particle shape plays a crucial role in the physics that finally comes out. And if you want to be able to probe the physics that comes purely due to activity alone, you would like to have a fixed shape in which you're able to tune activity in a very controlled manner. Okay. Now, what we are going to do in our group, what we've been doing in our group, is to basically exploit 3D printing. Okay, and 3D printing is something that most of us, or almost all of us, are familiar with, and the applications are just enormous. And you have 3D printing that comes about, and you can print aerospace parts. These days, if there's a failed part, you just print it out and replace it. 3D printing is not just there in automotive; it's there in chemical industry, where you're printing porous materials for removing toxic gases. This is a 3D printed aortic heart valve, dental implants, prosthetics, and bionic ears that have also been that people have also managed to print. What we want to do is to just 3D print active matter. Okay, and the goal, of course, is to be able to start with a very simple shape and start systematically putting in activity in a very controlled manner without altering the shape at all. Okay, so that then we can probe the physics of the system by just controlling activity alone. So, I already told you that if you have particles which have a friction or a mass anisotropy, you're going to get propulsion. So these are particles which we print out. These are like ellipsoids. These are ellipsoids, and during the print process, what we can do is we can basically put in a small friction asymmetry. So you see that this shiny part here has a lower friction, which is why it is it's a smooth surface, which is why it is also transparent. This rougher surface has a higher friction coefficient, and we can encode this during the print process. Okay. And this is what our plate looks like. So this is the top view of the plate. So we have about 8,000 particles in this particular field of view. And the advantage of 3D printing, of course, is that we can print thousands of particles in a single batch. And we can go down from, say, this ellipsoids that I show you here are basically 6 millimeters in length, 3 millimeters in width, and about 2.3 millimeters in height. But you can go down to much, much smaller dimensions, which means that this plate can accommodate as much as 50,000 particles. So this is really a macroscopic system in which we can really start looking at collective behavior. Okay. Now to tune activity, what we are going to do is something very simple. So I told you that if you have a friction and a mass asymmetry, you're going to get propulsion. But then what we are doing is that we're going to keep the shape of this particle constant, and all we do is during the print process we take this hole and we move it along the major axis. Okay, so we have a hole here and we systematically play with the position of the hole. And now in these sort of active systems, there are two key parameters that one wishes to control. One is, of course, the persistence time, and by this all I mean is once I head in a particular direction, for how long in time am I going to keep the same heading? Okay, so that's what's called the persistence time. And the other parameter that I'm interested in is the velocity of the particle. I should be able to tune both of these parameters for a systematic study on these sort of active systems. Okay, so let us see that whether this approach of ours, in which we are systematically altering the mass asymmetry, allows us control over activity. Okay. So let me show you a bunch of videos. So this is activity 1, in which I have a particle with the hole in the center. This is what you see. This is activity 2. I don't think you can make out much difference, but these particles are marginally faster. I'll quantify this soon. And these are activity 3, 4, and 5. Okay, and as you can compare activity 1 and activity 5, which are the extreme cases, you see that these particles are basically don't have very long persistence lengths. You will see that they make very quick turns, whereas these guys go in a straight line for quite some time before they basically make a turn. And just to say that this is a prototypical example of active matter, let's compare this with what a bacteria would do. So I'm going to show you a video of what happens in bacteria. So I would like you to follow this particular bacteria here. I'm also pointing out the trail, and you see that the motion of this bacteria is very, very reminiscent of what you see here. You have these straight paths followed by abrupt turns. So we really have a laboratory mimic of what's at least a single bacterium is doing. Okay. Right. So so now we can quantify this activity, and I told you that the two parameters that we would like to control are the persistence time and velocity of the particle. I'm just going to show you two very simple plots. So in these plots, I'm plotting something called as the mean square displacement. And if you are a particle that's traveling with a constant velocity, you know that your displacement as the square of the time. Okay, so that is why the slope is 2. So we call this ballistic, and you'll see that the mean square displacement is initially ballistic. And at very long times, when you have undergone enough collisions, you're going to go from ballistic to diffusive dynamics. And that time the slope becomes 1. And as you systematically change the activity, what you will see are that the persistence time, which basically marks the transition from ballistic to diffusive dynamics, systematically increases, and so is it with the velocity. Okay, so this profile that I show you of the velocity distribution of the 3D printed active particles is very characteristic of what you would see in a biological system. Like, for example, in bacteria, you will see this bimodal distribution, one that's got to do with the tumbling velocities, ones that got to do with the running velocities. Okay. So the first goal that we have managed to achieve is that in these designer active matter, the 3D printed active matter systems that I'm telling you, we can play with the persistence time and the velocity with keeping every other parameter constant. Now we can go one step ahead, and that's got to do with chirality. Okay, and we all know what chirality means. So if you're standing in front of a mirror and if you cannot superimpose the mirror image on the object by pure translations and rotations, you would call it chiral. The most familiar example of a chiral object is the palm of your hand, and this is a static property. By that I mean this is already encoded in the shape of the object by the constituents that make it. Okay, and chirality is something that's ubiquitous in molecular systems. For example, you know that amino acids are chiral. They are all left chiral. RNA and DNA are chiral. So there are also synthetic systems that you can make chiral. Okay, now what's very intriguing about chirality, or what's fascinating about chirality, is that whenever you bring in chirality in an object, you start bringing in selectivity. Okay, all I mean by that is whenever you have tried to shake a hand, you will see that two people will extend the same right hand or the same left hand. Okay, so just by being chiral, you bring in selectivity in the way things interact, and that's not just true with palms, it's also true with molecular systems. For example, you can start with the mixture of both left and right chiral molecules, and they will spontaneously assemble into either ones that recognize each other. So all the right-handed molecules recognize themselves and assemble into this sort of object, or you can also get discrimination in which a right tries to pair with a left. Okay, so being chiral brings about selectivity and recognition, and so it's a very, very powerful paradigm for organizing matter. It turns out that chirality is not just a feature of, it's not just a static property, but you can also have chirality in active matter. And by chirality in active matter, I'm not talking about the shape of the particle itself, but I'm talking about the handedness in the way they move. For example, if all particles try to move clockwise, you would call it chiral, and if they moved in the counterclockwise direction, it would be chirality in the opposite sense. And this observation of chirality in active matter was made almost 120 years ago. And this is a study that appeared in this journal called the American Naturalist, in which this microorganism called Loxodus was found to swim in a corkscrew type of a fashion. Okay, that's not just true with this system. For example, you can take the same E. coli bacteria that I showed you a little while ago, and if you are able to bring it near a surface, you will see that it executes circular trajectories of a well-defined handedness. Okay, and because of the fact that you are handed, you also start seeing these sort of self-assembly in which particles interact through their chiral interactions. These are all natural systems, and you can of course make chiral matter in the lab as well. And now, but predominantly, the chiral active matter systems that people make in the lab are chiral in shape as well. Okay, and for example, this is a chiral object, which is an L-shaped object. You will see this is a mirror image, but they have opposite handedness in their dynamics. Okay, now keeping in mind the original goal in which we would like to play with activity, play with chirality without altering the particle shape, the question is, can we design such particles? And just like in molecular systems, where being chiral means being selective and the ability to recognize each other, can we also see that in active matter? Okay, so we're going to go back to the ellipsoids that we were working with. Now, so this is the major axis of the ellipsoid. And I told you there is a friction asymmetry that gives you a forcing term. I also had a mass asymmetry, but both the friction and the mass asymmetries were along the same axis. Okay, now because of this, the forcing was along the major axis and the particle just moved in a straight line. But during the 3D print process, what we can do is to just move this hole a little bit along the minor axis. Okay, now I have two forces, one that is offset, and I would expect this to give rise to a torque as well, so that a particle, I would expect it to go around in a circle. Now, I don't have too much leeway in how much I can move this hole. So what I essentially do is to print this hole, but also etch out the interior of this ellipsoid. Okay, so I'm going to make it more and more hollow. So these are the ellipsoids that I print. And you will see that as I go from C1 to C6, this region is becoming less and less hollowed out. So this is the most hollow ellipsoid. This is the least hollow ellipsoid. Okay. Now, if you were to look at the dynamics of these particles, and you can see that they are beautifully chiral. For example, this is C2, which has the maximum mass asymmetry, and you will see that this executes very, very small circles. And as I systematically decrease the mass asymmetry, I go from these sort of small, short circular orbits to really large circular orbits. You can see this particle here. And these are not cartoons. These are images from our experiment in which we are able to, we are superposed images at various instants in time, and you see this nice circular orbits. Okay. Now, because we are doing 3D printing, we can start with any shape that we want, be it disks. For that matter, we have recently printed out these particles, which we call bananas. So these are bent core pneumatics. So there are molecular equivalents of these. We can impart a chirality or an activity to the system and look at how assemblies of these particles behave. Okay. So now let's do this experiment on this chiral active fluids, which is going to be the focus for the rest of my talk. And as you would already know, that the dynamics of a system is going to depend on the density of particles. Imagine yourself moving in a very dilute crowd, in a dense crowd. Okay, so the density of the crowd is going to determine how fast or slow you move. So we call that the particle number density, which we calling it by phi. And because I have chiral particles also, it also matters whether I have. How many particles in my system like to move left. How many particles in my system like to move right. So I'm going to define the net chirality of my system as basically something that tells you whether I have an excess of one particular chirality in my system. So a racemic mixture is one in which I have equal numbers of both plus and minus particles. An enantiomer pure system would be in which I have chirality of just one kind. And if I had excess of one particle, then I would call it an enantiomeric excess. Okay, so we can do this experiment. We do it in such a way that once we put particles on the plate, they don't flip, and we can now start looking at the dynamics. Okay, and this is what this experiment looks like. And you will see something quite fascinating happen, but I'm going to zoom in and tell you what happens. Okay, what we see in our experiments is something that's pretty intriguing. Okay, so let us say you had a particle which had a minus and a plus handedness. They just spontaneously come together and form this thing called as a mover, which we call a mover. Okay, and you will see that this mover state, okay, just survives for a very, very long time. And this is something that one can understand. Okay, we have seen this in many, many movies in which during a car chase, there's a person trying to drive a car to the left. There's a person trying to move a car to the right. Both of them come together and just move in a straight line. And that's this mover state. Okay. And now we can calculate the lifetime of these movers in our experiments. And what we find is that because of the fact that for the smallest chiralities, or for the smallest radius of orbit, you have a very, very large torque. It means the forces that are pushing the particles together are very large. The lifetime of those movers is also very large. And as you systematically start tuning the chiral activity in the system, this time scale comes down. Okay. But what is something that I've never seen in any action flick is this particular state. Okay, what we found is that you can take two of these minus particles or two of these plus particles, and they spontaneously form what we call as a spinner state. Okay, and this spinner state survives for a very, very long time, like the mover state again. And as you would see, this particle is spinning quite a bit, but it is not moving around in space. So translationally, it is immobile, but it has got a very high rotational activity. Okay, now just to tell you that the spinner and the mover states are not seen for all chiralities. we see them only for the shortest chiralities, for the smallest radius of orbits. And this is already telling you that in chiral active matter, if you're able to tune chirality in the manner in which we have been able to do so, you start seeing selectivity come about in the interactions. Okay. Now, the next question, of course, is can these particles also recognize each other? Okay, just like the palms of a hand recognize each other, can these particles that are just simple boring looking ellipsoids also recognize each other due to chiral activity alone? Okay, so I have two ellipsoids here. So the C2 ellipsoids have a very small radius of orbit. The C4 ellipsoids have a very large radius of orbit. And what you see is we're going to try combinations of these and see if the C2 and the C4 ellipsoids are longer lived than C2 C4, because that would mean there is some sort of recognition coming about in the system. Okay, so I'll tell you what we do. So we start with these particles, they form these sort of pairs, and they form these movers. Okay, so now what we do is we do this experiment many hundreds of times, and we, like earlier, we're going to measure the lifetime of these pairs. Okay, the lifetime is an indicator of how strong the bond is, so it'll have information on whether there is recognition. Okay, now the fascinating thing that happens is indeed there is one. For example, this blue line that you see here is basically C2 ellipsoids coming together, the lifetime of these ellipsoids, and you will see that that is around 14 seconds. This is C4 ellipsoids, that's about 3 seconds. But the C2 which are these particles which look identical, but which differ only in their chiral activity, have a much shorter lifetime. So what it is telling you is that these systems not only are selective in the way they pair with their opposite chirality, but they can also distinguish between other chiralities. Okay, just like you would in a molecular system. So the next couple of slides are what happens in the very dense limit, and I will just quickly go through this. Now, like I told you, in a racemic mixture, so you have equal numbers of these and these. But in a racemic mixture, because I have both the chiralities present, it means I can get both the mover and the spinner states. And as you go from a racemic mixture to an enantiomer pure liquid, you're going to in the enantiomer pure liquid, because all particles have the same handedness, you're going to get only the spinner states. So by just changing the chirality of the active system that we are working with, we expect changes in the dynamics. And this is to just tell you what happens. These are just movies about what happens for a given density as a function of chirality. And we can quantify what I call as a relaxation time. By relaxation time, all I mean is the time it took for a particle to move a distance comparable to its particle size. Okay, that's what I have in mind when I talk about relaxation time here. And what you will see is that what is spectacular about chiral active fluids is even if I were to keep the number of particles in the plate constant, but just change the net chirality, the dynamics of the system actually starts slowing down. So the relaxation times are growing. Okay, so it takes longer and longer for the system to relax when I change the net chirality. Okay, so why does this happen? And the reason it happens is what we do now is to basically start looking at how these particles move in a dense liquid. So the arrows here indicate the direction of motion of each particle, and the color codes are basically how much each particle moves. Okay, now at a given density, when we change the chirality, what you see are that the nature of relaxation is fundamentally different. For example, here you see this beautiful swirls come about. Okay, something that we have never seen, that's something that we never see in the other chiralities. Okay, and we can now quantify the size of these swirls, and you find that the size of these swirls gets larger and larger. So a larger and larger swirl is going to take longer and longer to relax, and that tells you why the system slows down. Okay, so this is one example of what controlling chirality allows us to do. And I also have to tell you at this point that the mover and the spinner states that we see have never been seen in any other active system, in experiments at least. And it comes about simply because of the fact that we're able to tune chirality and activity in the system in a very controlled manner. Okay, so the take home that I have for you is that 3D printed active matter or designer active matter allows us to tune activity in a very precise manner, and that should open the door towards experiments that can check theoretical numerical predictions. Encoding chiral activity in granules brings about selectivity and recognition, just like you saw in molecular systems, and also fundamentally alters dynamics. And what makes active matter fascinating is that it is at the interface of physics, biology, engineering, sociology, because about crowd control and panic, and even art. And I would like to leave you with this slide. So these are beautiful photographs taken by this person, Xavi Bo. What it's telling you is that if birds left tracks in the sky, they would look like this. Okay, and this particular form of art is called ornithography. Okay, for the fact that this is art made by birds. Okay, and with that, I'd like to thank you, and I look forward to interactions later on.
Thank you, Professor Ganapati, for this fascinating journey. And it's really amazing how all the things come together, like, biological sciences, physical sciences, and art. And we will come back with any questions which the viewers have at the end of the webinar. Thank you.
Thank you.
Now we go on to the next speaker, Professor Surajit Dhara. Professor Surajit Dhara is working at the School of Physics, University of Hyderabad. He is a PhD from Raman Research Institute, Bangalore. And then he worked as a postdoctoral fellow from the Department of Organic and Polymeric Materials at Tokyo Institute of Technology, Japan. And after that, he has been working in the University of Hyderabad. His specialization is in the field of soft condensed matter physics. And he is going to talk about topological defect and elasticity, mediated direct assembly of colloids in liquid crystals. And the title of his talk is Fun with Faults in Flowing Crystals. Over to you, Professor Dhara.
Good morning, everybody. Let me first thank Dr. Sekhar Mande and Dr. Geeta and also Dr. Mr. Mahesh for arranging this, and also entire CSR family for arranging this lecture. The title of my talk is Fun with Faults in Flowing Crystals. Let me make it clear in the beginning. What do I mean by flowing crystals? Flowing crystals are basically liquid crystals, and faults, I mean the defects. So usually, liquid crystals are used in liquid crystal displays. All the flat panel displays, they exploit liquid crystal. And they are fault-free, means there is no defects. In this talk, I'll try to sort of give you a flavor how these defects, which are unwanted in displays, can be exploited for new applications based on liquid crystals. Okay, so as we know that the crystals, in crystals, usually atoms and molecules are arranged in a regular fashion. So if they have a periodic arrangement of these atoms or molecules, when you heat these crystals, they melt beyond a melting temperature and go to an isotopic state where both this positional and the orientational order of the molecule is completely destroyed. So it's an isotopic liquid. Okay, and very often there are some organic crystals made of elongated molecules like this. When you heat, they go to some intermediate state in which, when they go from crystal to isotopic state, they lose their positional order, but they retain their orientational order. So you can see these long molecules, they retain their orientational order, but they have lost their positional order. This intermediate state is known as liquid crystal. In this state, as the name says, that they have both properties of crystals and also of isotopic liquids. For example, the physical properties of liquid crystals are tensorial in nature, meaning they are direction dependent. For example, these dielectric properties, conductivity, the elastic properties, optical properties, like crystals, they are anisotropic. And at the same time, these liquid crystals also can flow like liquids. They have viscosity and also surface tension. Here I show you one short movie that to show the fluidity of this liquid crystal. This is a room temperature liquid crystals, and typical liquid crystals which are used in liquid crystal displays. You can see that they are highly fluid. Of course, they look like a white fluid because they strongly scatter light. And this has viscosity almost 10 times greater than the conventional liquid like water. But they also have certain amount of elasticity. But the relevant elastic constant is so small that this is very useful for displays, because you can apply a small external electric field to deform the crystal. So as I said, that these liquid crystals are mostly used so far in all flat panel displays, starting from your mobiles, laptop, computers, even this cell phone, these cameras, watches, everywhere. The one common thing about in all these displays is that usually the liquid crystals are sandwiched between two plain glass plates, parallel glass plates, and the direction of liquid crystals, the orientation of these molecules is fixed in some specific direction. For example, the N is the average direction of these molecules. Sometimes we call this as a director, means the average direction of the molecules. And you can see that in the displays, the direction is usually fixed. That means there is no faults or the defects in the molecular arrangements in the liquid crystal displays. Now I will, in this talk, as I said, I will show you that how these displays, these defects which are unwanted in displays can be created artificially and used and exploited and exploited for practical new applications. So let me begin with the defects or the faults we know in solid crystals. In solid crystals, they are usually called dislocations, as we know that these are basically irregularity within a crystal structure that contains an abrupt change in the arrangement of atoms and molecules. But in case of liquid crystals, the faults which I say is basically defects. The liquid crystal, the defects are the mean direction of the molecular orientation that cannot be determined uniquely. Let me explain what I mean. Suppose you take a thin film of liquid crystal and look under optical polarizing microscope. You will see very beautiful and colorful textures like this. This is because the retardation varies in space. This is a birefringent material. And what if you carefully look at it, there are some dark lines moving around, and there are some points. And at that point, that these lines actually intersects. These points are actually the faults where the defects are located. The defects are very, very small, of the order of few nanometers. We cannot see them visually, but the far field deformation, because it's a liquid crystal, the far field deformation actually tells you where is the defect. Now, these defects can be associated with some kind of strength, what we call M. This M is basically the measure of the defect strength is that how many times these molecules can rotate around this point. For example, this is the defects or the faults or what you call the singularity. Now, if I go at 2 pi, how many times the molecule rotates? If they rotate 2 pi in the clockwise, we can say that they have defects of strength 1. For example, this is one typical example of a defect of molecular sort of orientation around defect points. This is the defect point, and the molecules are radially oriented, and this we say defect of strength +1. Similarly, if you have this kind of molecular arrangements in this around this point, and you can see this as you go clockwise, these molecules, these lines represent the molecular orientation, they are actually anti-clockwise. So these are called +1 and -1. Basically, this total defect strength is 0. They should be conserved. Now, you can also have M could be a +half or -half depending upon the sensor rotation. The point is that what I'm trying to make is that we can actually have spontaneous, again, such defects are unwanted in all liquid crystal displays because defects will create problem for your displays will not work. And therefore, they are of the line defects. So these green lines, these things are actually the molecules, representing the molecules, and the lines, the defect lines are perpendicular from one plate to the other plate. Now, these defects which spontaneously generated during the phase transitions can also be created. These molecules are on an average oriented in this direction. So these lines represent this uniform orientation of liquid crystals. Now, if I disperse a foreign particle, let's say this is a silica particle with some specific treatment on the surface, this particle, when you drop in these liquid crystals, remember the liquid crystal is the elastic medium. It will immediately create an elastic deformation in the medium. What kind of deformation they do induce? See, this particle, the moment you disperse here, they actually act as a source of a +1 defects, because we can see as if logically this charge has to be preserved. Therefore, this particle has to induce another minus charge very close to it. Therefore, the moment you draw, which can be seen under microscope. Here I show you some optical polarizing microscope, meaning this photo is induced by this silica particle. So this is a silica particle. If you see this unpolarized light, the normal light, you can see that this protrude, and here the defect point is somewhere here in the right side in this protrude, because topologically, they are equivalent. What do I mean? That you can actually push this point defect towards the particle when it goes to this surface to a ring which goes around the equator, and this looks like a Saturn ring. So therefore, it is called a Saturn ring defect. So it is possible that microscope, this is the typical size of this particle, around 5 micron. In fact, even several, you can much bigger particle or smaller particle can be dispersed, and these defects can be still seen. Now, size of the particles, and these forces are actually very unusual if you compare with the conventional colloidal systems, for example, water-based particles. There, the forces are mostly short range. It could be van der Waals, it could be steric, it could be coulombic. But here, these forces, the origins of these forces are structural. So I saw this one movie where these two particles, as you see, they approach each other because of these long-range interactions. So when the particles are collinear, they have long-range and attractive interaction. Of course, if the particle approaches from other angle, this interaction is actually anisotropic, meaning the interaction depends on how they approach, from which angle they approach to each other. So this interaction energy, you can see, could be order of several thousands kBt. Therefore, this binding energy for such this colloidal particle is very, very strong in liquid crystal. These structural forces have no analogs in any isotopic solvents. Now, this particle, as you see, they have a long-range attractive interaction or repulsive interaction depending upon their approach. We can use laser tweezers to direct their assembly. For example, this white spot is a laser light, and I trap these particles using a laser light and assemble them in a chain. And several chains can be brought together again using this laser tweezer. So this is a laser tweezer with a higher intensity. This white spot tells you that locally I melt liquid crystals and create some deformation which is felt by the chains. Now, essentially, you get a sort of two-dimensional assemblies. So how these structures are stable? You see that these particles are actually stable due to two competing forces. One force is the long range, which is attractive, which tries to bind this particle, but between them there are some defects. These black dots are the defects having strength of -1. These defects actually prevent them collapsing. Therefore, you have a long-range attractive and short-range repulsive, and the competition between these two forces actually helps them to stabilize these sort of two-dimensional assemblies. Now, not only this spherical particle, we can also achieve directed assemblies of particles with anisotropy. For example, this is a sort of linear chain of this spherical silica particle of 5 micrometer and a sort of nanorod, I would say, nano in the sense that the diameter is around 300 nanometer and length is around 5 micrometer. So you can actually bind these particles with a thin sort of silica nanorods. And again, these particles actually induce defects, so they are defect decorated, and the defects actually are existing between each two particles. So they are long-range attractive and short-range repulsive. Also, this is another figure where we show that this is a linear sort of chain of nanorod, microrod, nanorod, microrod. Also, this is on microrod, nanorod, sphere. So it's kind of a you can actually make a colloidal analogs of polymer chains of different types. The ultimate goal of such assembly is that can we make photonic crystals or the photonic bandgap materials? As we know that photonic bandgap materials, they are basically a periodic dielectric structure, and these structures are very interesting for controlling and propagating light. In fact, depending upon these lattice parameters, certain range of wavelengths of light can be forbidden to be propagated through this medium, and there can be one-dimensional, two-dimensional, three-dimensional photonic crystals. The major problem of such crystals is that they are not tunable. In the sense, once you make, you cannot tune the lattice parameter and hence the bandgap of these materials. The idea or the question which we are asking, suppose I use liquid crystals as a template and use this kind of spherical particles, can we make three-dimensional colloidal crystals? And as you know, since the medium is a liquid crystal, which can be deformed easily by a small external electric field, can we tune this lattice parameter of the crystals and the structure? That is the ultimate goal. But the point is that the challenges are how do we make such a three-dimensional control structure of colloidal particle? Now, here I will present some simple two-dimensional colloidal assemblies which we have made using this 5 micron colloidal particles, silica particle in liquid crystal, nematic liquid crystal. This is a you can see this is a picture of a two-dimensional assemblies colloidal assemblies of particles. And this colorful pictures because this is taken between cross polarizers, and the colors come because of the birefringence color of the liquid crystal. If you see in the unpolarized light, you can see that there are defects between two particles. Okay, so these particles are defect decorated, and we first make this chain, and then another chain anti-parallel way we arrange, and you can see this structure is very, very stable for several days and weeks. Now, so we have sort of achieved a two-dimensional colloidal assemblies in liquid crystals which are stable, and the typical binding energy for these particles is around 10,000 kBt. Okay, therefore the structure is stable. Now I show you an interesting effect. Suppose this structure is made in a simple liquid crystal which has only orientational order like pneumatic. But as you know, liquid crystal very often they exhibit various types of phases. For example, another simple phase is that symmetric phase where this molecule tend to segregate in a layer. And there are many liquid crystals they exhibit this kind of phase transition. Now I make this 2D colloidal crystal in the pneumatic liquid crystal, and as I show you what I do, I just decrease the temperature of the system. And you can see there is a change in lattice parameter. Okay, and then eventually when you go to the other phase, you can see that the crystal structure tend to collapse, and you have got different types of lattice parameter. So what I'm trying to tell you is that we can actually tune the structure and the lattice parameter of these two-dimensional assemblies going around this phase diagram. Okay, and there are several phase transitions possible. Therefore, it is possible to achieve different types of colloidal two-dimensional assemblies with different symmetries and structures. Now, the structure which I made in the previous slide I showed, those structures actually made of particles having defect strength of -1. As I said that it is also possible to induce defects of defined strength. For example, this is a schematic example of a particle having a ring defect. The strength of this ring defect is -1. And if we have a large number of correction, we can use a laser tweezer and to direct this to make a two-dimensional assemblies. This is a simple example of a simple two-dimensional assemblies of this 2D crystals made of colloidal particle with Saturn rings. And you can see the structure is very different than what I saw in the previous one. And lattice parameter are also different. The symmetries are also sometimes different. In this picture, I saw that if we have a defect of -10 to strength -2, it is possible that two such particles can be bound and made a dimer. So these defect rings actually bind these two particles and form a dimer. Such dimers can be assembled to make again a two-dimensional assemblies with totally different lattice parameters and the structure. The important point about this structure is that this structure actually, I apply the electric field perpendicular to this, you can see the structure is tunable. And its lattice parameter can be tuned more than 30-35%, which is remarkable because this is not possible in any conventional crystals, the soft crystals which we can design. And similarly, that not only by electric field, if we apply or if we change the temperature of such this crystal, you can see here that what I do, I basically decrease the temperature and again go around the phase transition. What happens? The lattice parameter again, these crystals tend to swell, and then there's sort of a collapse transition, but the symmetry and the structure of these two crystals are very different. Therefore, what I'm trying to present here is that it is possible, exploiting the defects of the liquid crystal induced by a foreign particle, it is possible to make two-dimensional assemblies. And it will be interesting now. The next step is to how to make a three-dimensional assemblies for this sort of 3D tunable crystal. So this is an example of 2D crystal, but it is not difficult. We are actually on the job that we are trying to make such layers and then arrange the layers on top of other and try to make a three-dimensional assemblies. And what the interesting part is that these crystals will be tunable much, and the tunability will be much longer than so far known in the literature. Now, in the next talk, in the next part of the talk, I will present some another aspects of these particles, and this part of this has already been sort of said by Dr. Rajesh Ganapati. The motivation for such work is that can we make these particles motile in liquid crystal? Can we control the direction of motion? Because as you know that for example, these are the two movies of the active particles, the active microorganism. These are called chlamydomonas algae, and these are E. coli bacteria. And you can see when the density is small, they basically swing. And these particles, they consume power from this environment, and they continuously move, and the system is out of equilibrium. And as we all know, the such system has been a subject of intense study in the present days, and many things already Rajesh has said and so on. So my question is that, can we artificially make microswimmers where we will have a control, precise control on the direction of motion? Okay, that is the sort of idea. Now, with this in mind, the one way to make this artificial microswimmer is that exploit what is known as electrophoresis. Let me tell you briefly what electrophoresis means. Suppose you have a charged particle in some electrolytes, and this charged particle, let's say, is negatively charged. It will induce, when you apply electric field, a DC field, it will induce some positive charges. And when you apply the field, these positive charges tend to move in this direction, and therefore it drags the fluid around, and the particle moves in the opposite direction of the field. This is called linear electrophoresis, and the velocity of this fluid and the particle is basically proportional to E. And this zeta is this sort of surface potential, what we call the zeta potential, and these are sort of constant material parameter. The point is that it's a linear electrophoresis. The particle moves with the velocity E opposite to the field. Now, suppose the particles they have no charge. Let's say metal particle. Now, these particles are highly polarizable because they are metal. The moment you apply electric field, then these particles become polarized. Let's say plus and minus. These charges, the bound charges, induce another charges here, and these charges are free charges. They can move under the external field. Therefore, this potential which you generate around the particle, is the zeta potential is given by A and E. E is the applied field. So you apply electric field, basically polarize the particle, and that polarized charge tend to move under the field. Therefore, it is E square effect. Okay, and in such cases, what happens? This the flow pattern around the particle is look like this, and these are called induced charge electrophoresis. And so flow is quadratic, but the point is that since the flow has a symmetry, if I see in this plane or in the other plane, they have a symmetry. Because of the symmetric flow, this particle will not be transported. They will not be mobile. Now, it was shown nearly 10 years ago that if you use a liquid crystal instead of water and disperse such particles, the liquid crystals, in the liquid crystal, these particles induce small defects. Let's say this is a particle inducing point defect. And liquid crystal also has some ionic impurities. And when you apply electric field, such defects also create what is called induced charge electrophoresis. Okay, this kind of flow. But these point defects, the location of the point defects here breaks the symmetry of this flow. So flow in this side is weaker compared to the back side. Therefore, this particle is moving forward. So you can see this is sort of a particle image velocimetry. This arrow shows how the fluid flows around the particle, and the particle moves in the forward. But in this case, the particles with the point defects, their motion is restricted in this direction only. So they have only bidirectional motion. We do not have control on the particle motion at our will. The question is, how do we make this particle controllable? If you look at, in fact, it was also said that if you have a particle this Hatton beam, the defects is the ring defects. This again, the flow around the particle is symmetry. You can see these arrows shows the fluid flow patterns, and the flow is, there are 4 vortices, and the flow is symmetric in this plane and that plane also. Therefore, the symmetric flow will not make the particle mobile. What I'm trying to say is that particles with the ring defects in liquid crystal will not be mobile. The question is, how do we make them mobile, and how we control the direction of motion? Then we thought, okay, let us break the symmetry of these flows. The one way of breaking the symmetry of these flows is that we we coat the half of the particle, the silica particle, half side we coat with a metal, thin layer of metal. In this case, we coat titanium. And so half is dielectric and half is metal. On top, we give some sort of coating of iron, the monolayer coating. So this liquid crystal can be oriented in a specific manner. And this is the side view and top view of this particle. And such particles, which is basically a metal or dielectric particle, half side is metal, half side is dielectric. These particles are actually known as Janus particles, in the name of Roman god Janus, which is having 2 faces. One sees the future, other sees the past. So these are basically very popular kind of particles. Now we disperse these particles in liquid crystals. Then what happens? This is a liquid crystal, and this is the direction of the alignment of the molecules. These particles in liquid crystals will induce ring defects. As you see, that these particles, the red circles are the defects. Now, when we apply electric fields, these particles start moving in the plane, and we look at the sample from this perpendicular direction. This particle is moving in the y direction, and this particle going in the negative y direction. Please look at this metal dielectric interface is parallel to this x-axis. This particle, metal dielectric interface is making some angle, nearly 45 degrees. In this case, the particle, the metal dielectric interface is making around 235 degrees. And in this case, it's around 315 degrees. And for particle 6 here, it is making around 45 degrees. And for the other particle, when this metal dielectric interface is parallel to y-axis, this moves in this forward direction. So what we notice is that the particles either sometimes. Now, if you look at this summary of this motion, what we find is that we can define a genus vector, what I say yes, which there are different types of orientation possible from 0 to 356 degrees. And depending upon the orientation of this particle, the particles actually can move in this S. Is in the x direction, it will move in the x direction. If the genus vector is in the negative x direction, it will go in this way. If the genus vector is in the negative y direction, it goes this way, or it goes this way. So the point is that this, by choosing the appropriate possible with any other conventional colloidal systems based on isotopic liquids like water. Okay, good. So we have achieved the control on this omnidirectional transport. We have achieved the omnidirectional transport. This is important for the control, transport, delivery, and also the collective behavior. Let me show you in this first movie how the direction of this particle can be controlled remotely by applying this, by varying the field amplitude. So in this video, in this movie, I am showing that this particle, see, whenever I change this electric field from some 1.5 to 2 volts per micron, the particle is changing its direction of motion. You see, it's going here, then again it is going in other direction. So if you look at this, where the trajectory is shown, when I change this electric field from 1.5 volts to 2 volts per micrometer, the particle moves this way, and again it goes this way. So these are the points where it changes the direction. The point which I am trying to say is that if we change this amplitude of electric field, we can control the direction of motion. Similarly, by changing the frequency, for example, this is one diagram where I'm showing, by changing the frequency of this applied signal, the electric field, from 30 to 50 hertz, the direction of motion can be sort of controlled. Now, I saw another movie where I have a target. Let's say this is the red star is the target. Now, I want to divert this particle to the target, and by simultaneously varying this amplitude and frequency, so you can see that this particle actually is going this way in this trajectory, and ultimately reaching to the target what I have decided. Therefore, this is a very precision control, remote control on the particle trajectory. And please note that this exploits liquid crystals, anisotropic conductivity, defects of the liquid crystals, and of course this asymmetric surface of the particles. Now the question is, how do we sort of understand? We looked at the theoretical aspect of this experiment without going much details into the theory. I will briefly tell you what actually we discovered. So let us look at this particle, and these lines represent the liquid crystal's molecular orientation. So field is around the z direction. We look at two orthogonal planes, namely the zy plane and zx plane. So what we find that since it is a metallodielectric particle, the metal side is highly polarizable. Therefore, when you apply electric field, the induced charges on the metal side is more. Therefore, the charges on the metal surface is also higher, and those charges will drag the fluid in this direction. Therefore, the flow of field will be stronger always on the metal surface compared to the dielectric surface. Okay, but what is important is that in the xz plane, in this plane, this direction of flow is towards the particle. Okay, and whereas if you look at the other plane, which is that yz plane, the direction of the flow is stronger on metal, but the direction is opposite to that. And so, in fact, overall, if you see this flow, which is given by these arrows, is sort of away from this particle. This kind of flows of the particles are called pullers, and this is called pusher. This is this fluid is pulled in towards. This is in this case the fluid is pushed out. And in this case, you can see that this arrow shows that when the flow is stronger in the metal surface, this will move in making a dielectric front forward. In this case, the fluid flow direction is opposite, is stronger, but it is opposite, that makes the particle to move in this direction. Therefore, the omnidirectional transport which I have observed is basically due to this combined effect of this pusher and puller flows. And coming to this living organism, which was our sort of goal to achieve the controlled transport, this kind of flow has been seen in case of chlamydomonas algae. You can see that they exploit this flow like this. In fact, these flows are around them is generated by this flagellum, and these are called puller type, and the E. coli they are called pusher type. Therefore, what we discover is that the particles which are dressed by the defects in the liquid crystals and also having asymmetric surfaces behaves like a combined puller and puller particles, which is seen in living system like in algae and bacteria. So the point is that, so we are trying to say that we have actually achieved particles. Not only we can have omnidirectional transport, but also we can control the direction of motion remotely precisely, which mimics the motion of the living microorganism. The ultimate goal is that now suppose I have a collection of large numbers of such particles. What do we expect? Of course, we expect some kind of collective behavior, and some of the videos which Dr. Rajesh has shown you. So therefore, we can have a controlled experiment in the laboratory on this artificial living microorganism and discover many more effects, which are in general not always possible to do on living systems. So to summarize, I would like to say that we have shown that these defects of liquid crystals, which are sort of undesired in display, can be exploited for making some new applications, for achieving long-range tunable interactions and directed assemblies, which are very, very important for designing tunable photonic bandgap material. We have also shown that the particles, this motility can be controlled by external fields, and not only that, we can actually pilot their direction of motion at will, which is very remarkable, and because it's very useful for controlled transport, active matter, and so on. Finally, what we felt is that this study actually opened up unexplored direction in controlled transport assembly and collective behavior. So possibilities are more, and we are actually going to do much more experiment in the coming days and hope to discover many more effects in these artificial moving microorganisms. And I would like to thank all of you for your attention. And I must acknowledge the supports from DST, SAR, CSIR, and my students, Zohail and Dinesh, who did the work, and Swapnil and Sriram from ISC, who worked on the theoretical part of this microorganism. And finally, thank you for your attention again. Yeah.
Thank you, Professor Zara. If you can stop sharing your screen, then we can, yeah. So thank you both the speakers for the excellent talks and taking us through the fascinating journey of physics. So there are a few questions from the speakers. Since Professor Dara just finished, I think I will just take his questions because it will be the flow will be maintained. So Professor Dara, the question is, any measurements have been attempted to measure the refractive index contrast?
Of the liquid crystal or the particles?
It isn't mentioned over here.
Yeah.
Okay.
So
maybe I will. I'll just read the comment before that. Then it may help you. Yeah. So the comment is: in addition to the lattice constant variation, it appears to me that the refractive index contrast also varies due to the variation in the number of LC molecules in between the spherical particles. So that was the comment. Following that was the question.
Yeah, but, it's a good question. The point is that when we have a liquid crystals are birefringent materials, okay, so therefore they have an anisotropy in the refractive indices. Now, when they are uniformly aligned, we get this birefringence, but the moment we disperse these foreign spherical particles, they create elastic deformation. They create deformation. Therefore, what happens? The birefringence and the resulting retardation changes. Therefore, we get a color. Yes, so therefore the point I'm trying to make is that, yes, what we observe in the colorful texture is that is basically a spatial variation of retardation, okay, around the particles. Yes, I hope I have answered that question.
Yeah, thank you so much. Professor Ganapati, are you there?
Yes.
Yeah.
Yes, I'm here. Yes.
Yeah, there are some questions for you as well.
Yes.
Probably the context is something which you'll have to figure out because it's they type it and when they're hearing the talk. Yeah. So unfortunately, I will not be able to provide you the context. But how other shapes will influence the dynamics?
Okay, so so we started with ellipsoids. Now, you see, even if you take, your long rice grains in your house and you put it on a plate, there's a natural tendency to align because you have these long objects. Now, clearly that sort of orientational order, which develops because you have a long shape, is not going to be there when you have, let's say, spherical particles. So, which is one of the reasons that when we did these experiments, we wanted to keep the shape as far as possible a constant and just control activity alone. Because changing the shape influences the ordering, even if you didn't have an active system. Yeah, so we expect the shape to play a very, very important role in this. Yeah.
Yeah, thank you. So the next question is, can we observe similar pattern of movement with other microorganisms? Perhaps you showed E. coli and few microorganisms.
Right. So yeah. So in the second talk, when Dr. Dara was talking about Chlamydomonas, I think you see these sort of organizations come about even in dense assemblies of other microorganisms. It is not limited to bacterium alone. So in my slide alone, I had one more example of a bacteria called T. majus, which once again forms these sort of beautiful spinner assemblies. And just like E. coli, they also do the same thing. So it's not specific to any particular bacteria. Yeah.
Yeah. Then another question is, how do you rate chiral aromatic molecules in day-to-day life?
It's well outside of my comfort zone.
It's okay.
That's a sixer. I'll tell you because what happens is that I don't know who has asked the question, but I'm just rating the context the question would be asked. Self-assembly is one of the very critical aspects in the evolution of everything, right? From the molecules to life forms, and from single cell lives to multicellular life. Self-assembly is critical. Now, in the chiral molecules, it is known that actually they do show a tendency of forming long kind of head-to-head assemblies or something, or which have reminiscence of long polymers or something like that. Yeah. So it's possible that the question is probably asked in that context, that do you see even at a molecular level some sort of collective behavior in that sense?
Okay, thank you, Dr. Mande. In the slide that I had, I did have an example in which people were able to assemble a supramolecule by exploiting chiral interaction. So the example that I had was indeed of self-assembly being mediated or brought about in a much richer fashion by introducing chirality. But I don't know enough about that literature to specifically answer this question, but that is something that people have been exploiting. And what we wanted to do is take that concept, which is very well known, and see if you just add chiral activity, no shape chirality, just chiral activity. Can you bring about these sort of assemblies? And at least at the level of dimer formation, we seem to be seeing selectivity. Now the question is, can we go to more complex assemblies? And that's what we are working on currently. Yeah. Okay.
So the last question to you is, why chirality favors spinning motion over translation motion?
Okay. So when I had the friction and the mass asymmetry all collinear with the particle major axis, then the driving was along the particle major axis, so they moved along a straight line. But now when I moved the whole along the minor axis, what I also did is I had one force along the particle major axis, but I also had a force that was slightly shifted. So that was giving rise to a torque. So now I know when I have a torque acting on the system, I have to cause some amount of rotation. So I had both translation and rotation coming about because of the way I forced the particle. Yeah.
Okay. Is chiral activity in molecules time limited?
So when you're talking about a static property, in which means in which the encoding is done in the organization of the interior of the molecule, it's a static property. But in our experiments, as long as we are driving the system using a plate, they are chiral active. The minute you turn off the shaker, they will just be ellipsoids on a plate. You will not be able to tell anything about it, whether it is chiral, achiral, nothing. You just will know that it is just an ellipsoid. Yeah.
Okay, so there's one common question to both of you. I think excellent basic research. How will it be able to make India Samarth Bharat? I think each of you can take that question.
So should I ask Surajit to go first?
Get ready. Welcome to the real world. So get ready to answer these kind of questions.
Professor Surajit, maybe you can take the question.
Sorry, can you repeat? I didn't get your question. Sorry.
Yeah, the comment was excellent basic research. How will it be able to make India Samarth Bharat? Or
it's difficult. Okay, so the point is that, of course, if in my presentation I mentioned that while our interest is, of course, is basic, but ultimately we have a bigger goal to achieve. For example, when I was giving the talk, I was saying that what is the ultimate goal? For example, I was talking about the tunable three-dimensional band gap materials, which has not been sort of realized so far. So if we use this if we use our approach and are able to make this tunable sort of the band gap material, that will be a big discovery. Okay, and therefore will be, and that will have various practical applications which actually people have been wanting for several years. So I think if we pursue this basic research with a ultimate goal, clear goal. Similarly, the second part I was trying to say that for targeted delivery or controlled transport, these are very common to even in biology, medicine, everywhere. So how, if we understand this in the basic level, then we will be able to design such particles and understand in the lab, then bring it to the industry level. And so where we know the mechanism, how it works, and that we have a complete control on this. So it's complete control on this mechanism, and understanding of the mechanism and the control on this particle trajectory motion is very, very crucial. So therefore, the more the kind of work which we are doing actually in the frontiers of this research. So by doing so, we are able to sort of discover new effects, and which we eventually, the time to come, will be useful for many applications.
Yeah, thank you. And I think you also had some technology. When I saw your website, Professor Dara, I think you've also been developing some technologies as well.
Yeah, okay. That's a good. Let me point it out. So thank you for pointing out. Actually, when I joined University of Hyderabad, I was working on liquid crystals. And during my PhD days in Bangalore, that I have seen that manually these substrates are handled for aligning liquid crystal molecules, and which are not really very reproducible. So when I joined, and I thought, okay, I should design some machine which can do automatically and make my things very simple and also very reliable. And so it took almost 3 years for me to design, and then I designed the machine, and then asked that Hallmark in this Kerala to make the machine. And with their help, we developed the machine, and that machine I'm using for last nearly, I would say, 14 years. And it so happened that this machine is now exported, marketed by Hallmark, and almost 10 countries it has been already exported. And so, in fact, that is how it is. So the machine which we basically designed for my experimental purpose has become a commercial product now. So this is very useful for industry, and I hope this will be very useful not only for this basic research, but also that is used for actually making displays, portable displays. Yeah.
Thank you so much. So Professor Ganapati, over to you.
Yeah. Thank you. So I had some time to mull over this. I don't mean to pat our own back here, but I'll tell you that our approach towards realizing these sort of active systems in the laboratory with such a sort of control, I would like to say these are the first sort of experiments in which you bring in this 3D printing technology, which is being used extensively even here all over the world, and then you bring it into active matter. And thanks to my student Pragya, whose perseverance and commitment towards doing all of these things, he is now able to achieve a sort of control in these sort of active systems, in which we can rival simulations. In simulations, they would just take a particle shape and they would say that, hey, I'm going to play with chirality, I'm going to put in activity. But in experiments, it's really been very, very challenging and they will have predictions for a particular particle shape. Now we can just print it out in the lab. And this is something that's being done for the first time, as far as to the best of our knowledge. And like I said, active matter systems, I probably went too fast over that example I said. in which people are trying to model, say, escape panic or crowd control. And, in India, there is no dearth of those situations, in which you like to manage crowds or organize things in a manner in which flow of people is more streamlined. And active systems, the ideas coming out from active systems are very, very indeed useful there. For example, in that nature study that I was telling you, they found that, if you had an opening through which a lot of active agents have to come out, to prevent clogging at the orifice, all you had to do was to put in a pillar in the middle of the door, and that would allow you to, suppress stampede. And in fact, there are experiments done not too far from where I work in Professor Ajay Sood's lab, in which he has looked at active matter escaping through small orifices. And these are all motivated by, real world challenges. And these are all very simple mimics, and now when you can start controlling the nature of activity, I believe they will have far-reaching consequences.
Yeah.
Geeta, can I answer that question too? Because if you can, I can chip in to reduce the discomfort of both the speakers.
Yeah, definitely.
Because I have bombarded with these kind of questions all the time. And also chip in a bit of thing. So definitely. I want to give two very good examples in India, how basic work, fundamental basic work of very outstanding quality has led to something towards Samarth Bharat is what was the question about, right?
Yeah.
And one of the examples pertains to IIT Kanpur work, Manindra Agarwal's work, where he did some fantastic work, given a very large number on prime number, whether it's prime or not or something, how do you find out an algorithm? And an outstanding work. I mean, the absolutely outstanding piece of work. Of course, he is very famous, but nonetheless, it has consequences on many different fields. For example, cryptology, whether you have your computer passwords and all, and are they sufficiently cryptic or not, can be actually done from this prime number theory that Manindra Agarwal has done. So both outstanding fundamental work in the lab, as well as towards making Samarth Bharat or whatever, both actually one thing. The more recent example is of our Feluda test kit. The group working in IGIB, they had a paper in Proceedings of National Academy of Sciences USA 2 years ago when they discovered this particular enzyme called Cas9. And today, in the COVID time, they have come up by the application of this enzyme into converting into a world-class diagnostic kit, the paper-based test. I mean, this COVID Feluda that all of us have been hearing about in newspapers and TVs and all over. Once again, fantastic piece of work, fundamental work, which is published in one of the frontline journals. At the same time, its application towards making a diagnostic kit and a completely Indian thing, so it's whatever you called Sashak Bharat, Samarth Bharat or whatever, everything is covered in there. So it's natural to expect that any fundamental work that is done, which is very exciting, one day or the other, it will actually find its way into the field for benefit of humanity. So we have to actually remember that anything that we see in the field today, any technology or whatever, is always backed up by some outstanding science that has been done in the past somewhere. So that we have to remember.
Yeah, very well said, Dr. Mande. Do you have any other questions to the speakers? Because the questions from the audience is done. So if you would like to...
I just wanted to ask both of them, because it's a general audience here. Can you recall your early motivations to come into science and how do you decide to choose this area and so on and so forth? That's a general question that everyone asks, so.
Yeah, Professor Ganapati, you're mute. Please unmute yourself.
Yeah, sorry. Okay, so as a child, I would like to tinker. I used to, meaning it was not very well received at the home because I would open up radios and TV sets. But then I used to love to tinker. And then after my master's, I actually used to work in Hindustan Lever. I worked for a year in the department called laundry cleaning. So we used to make soap and especially surf. And that got me into soft matter, actually. And then when I joined IISc for a PhD, I was naturally drawn towards Professor Sood because he was doing all of these experiments in soft matter. And there it goes. So it all started with tinkering at home. So, yeah.
When did you join? Because I might have overlapped with you, no?
I joined IISc in 2000 for a PhD.
He's much younger.
I'm too old.
Professor Dara, would you like to answer the same question?
Yeah, actually, from the childhood, I wanted to be a science teacher. And so after MSc, when I wanted to do PhD and join Raman Institute, the thing which attracted me is that liquid crystals, because for me, I was very sort of fascinated by the name, how a crystal be liquid. So then joining the Raman Institute and spending some time, and then I really found that this is a beautiful world, and so I got into more and more into it, and that is how I started working. And so in fact, then later on, of course, when I joined the university, as I told you that I wanted to be a teacher, so I wanted to remain in the university for teaching. I love teaching to students, and while I teach, I also develop my lab and do some research. That is how my passion has been, and I am carrying it now also.
Yeah. Thank you so much, both the speakers. It's really a fascinating journey. I am a biologist. I don't know much about physics, but I really see how things come together. This series has really helped us. I see chemists talking about biology, and you are talking about E. coli movement and crowd, Kumbh Mela. Maybe we can design better Kumbh Melas with this. I mean, the applications are enormous. I think that's what is the goal of this. And I'm sure the viewers would have really enjoyed, and get fascinated by the excellent science. And I think, like Dr. Mande said, excellence is what is important, whether it's basic science or applied science. And I'm sure this audience would really have enjoyed this talk. Thank you both for sparing your time. And thank you, Dr. Mande, for joining us. And I would like to thank Mahesh and Deepak who are helping us with this whole event. And thank you, all of you. And next week, probably we come with the engineering sciences. Thank you again.
Thank you.
Thank you very much.
Thank you.